Okay, so last time we had finished up looking at calculating pH for weak base situations. Now we're going to look at conjugate acid-base pairs again. We talked about these in Chem 111, and they were defined as components that are different by one proton. The conjugate acid has one more proton, the conjugate base has one less proton. When we have strong acids and strong bases, their conjugates don't exhibit acid-base behavior. So, for example, if we had hydrochloric acid, a strong acid, and we put it in water, it breaks apart completely. We have this one-way arrow, and it makes hydrogen ions and chloride ions. And it doesn't go back. Those hydrogen ions are floating around in solution. The chloride ions are in solution. This chloride ion has no interest in picking up a hydrogen again. It just sits there, and so we would have hydrogen ions in solution, and it would be an acidic solution. But when we have a weak base or a weak acid, it's kind of different. So our generic weak acid is HA. It's in equilibrium, H plus and A minus. So this A minus is interested in re-hooking up with that proton to go back and make HA. So in this case, we started off with the acid, and we have it dissociating and reassociating in equilibrium. But what happens now is the A minus is the conjugate base of a weak acid. And because it can pick up a proton, that makes it a base. So we're going to look at now what happens when we put these conjugate bases of weak acids into solution without coming from the acid. Because we talked about acetic acid as our classic example, this is the acetate ion. The acetate ion can be part of a salt. So if we put a salt in water, now you have this A minus, this conjugate base. It can act like a base, and it'll actually make the solution basic. So that's what we're going to look at next, is acid-base behavior of salts because they come from these acid-base conjugate pairs. So if we look at this relationship in the acid-base conjugate pair for hydrochloric acid and chloride, which I just said, I've put it here showing water in there where we have H3O plus instead of the H plus. That's just how the textbook does it. So this is not interested in going back. But when we have a weak acid, then it is. So let's look at this acetic acid equilibrium. We have acetic acid plus water making the hydronium ion, and we could leave the water out and just have H plus here, but the textbook likes hydronium, plus the acetate ion. And we can determine Ka for this. It's the concentration of the hydrogen ion or hydronium, they represent the same thing, times the acetate concentration. You can see with all this writing why I just like to call it HA. Divided by the acid concentration. Now, let's look at what can happen with the acetate ion by itself. This is what's going on with the acid dissociating. But if I put the acetate ion in water by itself, where I don't have any acid in the beaker at the time, it can react with water in equilibrium to make a hydroxide ion and the acetic acid. So one of these protons is hooking up with the acetate ion to make acetic acid, and I'm making a hydroxide ion. So this conjugate base of the weak acid exhibits basic behavior when it's placed in water. And we can write a Kb for this. That's equal to the hydroxide concentration times the acetic acid concentration divided by the acetate. Remember, we leave water out because it's a pure liquid. So we don't put it in our equilibrium expression. So we can see how that conjugate base can behave as a base. Now, let's take these two equilibria and add them together, just for kicks. So if I take the acid equilibrium, do you care if I just call this HA now to make it easier to write? Okay. So we have the first one, HA is in equilibrium with H plus A minus. And we have the second one, A minus plus water is in equilibrium. Well, I guess I should add water here too. Otherwise this doesn't work. So I'm going to make this H3O plus. Otherwise this doesn't work. And then add the water there. Then A minus plus water is in equilibrium, which H3O plus HA. So now, if we add these two equilibria together, this is not right. Hydroxide. See what happens when I go off script? Okay, so now when I add these together, I get water plus HA plus A minus plus water is in equilibrium with H3O plus A minus plus HA plus OH minus. Now, if we look at this equation and we go ahead now and cancel out what appears on both sides, I have 1 mole of HA on each side. I have 1 mole of A minus on each side. So when I combine the acid equilibrium with the equilibrium for its conjugate base, what I'm left with is 2 waters is in equilibrium with H3O plus OH minus. And that's the autoionization of water equilibrium. So now let's look at what happens with our K values. Remember back in chapter 15 when we talked about multiplying things together and adding equations and manipulating K values. We said that this was represented by Ka and this is represented by Kb. So when we add these together, we can multiply together the equilibrium constants. So my new K is equal to my Ka from before, H3O plus times A minus divided by HA times the equilibrium K, the Kb, OH minus times HA divided by A minus. Now when you look at this, we can cancel out what divides. We have HA divided by HA, that cancels because it's 1. A minus divided by A minus cancels because that's 1. So we end up with my new K is equal to H3O plus times OH minus. And what K is that? We gave this a special name previously. It's the water, right? So it's KW. So what this has taught us is Ka times Kb is equal to Kw for an acid-base conjugate pair. So now this gives us the ability to do calculations with a conjugate base of an acid. If we know the Ka for that weak acid, we can find the Kb for its conjugate base. So for any acid-base conjugate pair, Ka times Kb is equal to Kw, and pKa plus pKb will equal pKw. And we assume we're at 25 degrees unless we say otherwise. Is that just somebody whistling or something? Okay. It's not an alarm, right? Yeah, because my hearing is a little muffled. Okay. So let's look at a problem. The Ka for formic acid is 1.8 times 10 to the negative fourth. What is the Kb for the formate ion? Well, formic acid makes the formate ion. You remember from Chem 111 nomenclature, ic acids make 8 ions and us acids make ite ions, right? So we know that Ka times Kb is equal to Kw. So Kb for the formate ion is equal to Kw divided by Ka. Since it doesn't say anything about temperature, I'm going to work at 25 degrees. Kw is 1.0 times 10 to the negative 14th divided by Ka, 1.8 times 10 to the negative 4th. And so that's equal to our new Kb for the formate ion, 5.6 times 10 to the negative 11th. So now, just for kicks, if you think about this, the Ka for formic acid is 1.8 times 10 to the negative 4th. The Kb for the formate ion is 5.6 times 10 to the negative 11th. Of those two species, which is more active acid-base-wise? Which will have more effect, the acid or its conjugate base? The acid, because it has a bigger value. Okay? Later on, we're going to have to think about that. Okay, go ahead now and do this next one. Let's go ahead and have you get out of your seats, do this on your whiteboards.